Okay, so this is our lecture on multiple linear regression, and this will be probably a little bit of a shorter lecture than the other lectures because we'll be doing a lot of multiple linear regression work in our in-class demos. So we'll kind of just go over the general ideas and concepts here, and then we'll go through and evaluate more of them in in-class demos. So we'll look at how multiple linear regression works a little bit. We'll talk a little bit about how to interpret parameters and the results of your linear regression model. We'll do a lot more of that in class. And then we'll look a little bit at feature engineering and how you do transformations of your features. Of course, always please ask any questions on the lecture material you have in our online forum, and we'll answer them as soon as possible. But okay, so thinking back to what we've been talking about, just as a quick reminder, we were trying to, well, first we had this idea that we were trying to predict the amount of time it takes to get to school from home, and that's in minutes. And we had this one variable, departure hour, and we decided to add another variable, day of the month. So just to recap, minutes would be what you're trying to predict, or your dependent variable. And then departure hour and day of month are your features. And just do a little bit of a recap here. Incorporating the multiple features is where we're going for multiple linear regression. So to begin, we just had our predicted commute time based upon one intercept and a slope with one of our independent variables. Of course, we added a new variable to that, and I suppose we can list these as this being our one input variable or input feature. And now we have two input features. And also worth noting that we have W0 in both of these, and we had W1 over here and W1 over here, and now we have this new idea of a W2. So these are the weights that we're going to learn, which will, by the process of minimizing the mean squared error for our multiple linear regression problem, and this will help us determine what the best fitting line, or in our case now with multiple feature input features, the best fitting plane. And we find the W star vector, or the parameter vector, which is made up of W naught, W sub 1, W sub 2, again by solving the normal equations. So let's put that normal. And when we think about, I mean, this is, I'm going to blast through these recap pretty fast because you're also watching these lectures most likely back to back since we're not doing them live. But again, when we have just one input feature and then one y-intercept, this is going to look like a line. Whereas as we add more of these things, more input features, we get into more complex objects. So in this case, with having a W2 and a W1, we're going to go ahead and have a plane versus just a line. Note they'll both still have W naught because there will be an intersection along the y coordinate. And if you think back or remember back to at the Math 20 series, you would see an equation that might be something along the lines of, I guess it'd be like z equals ax plus by plus c. In this case, your c, your W naught, and then your ax would be that, and your by would be this. And yeah, it's not, it's just rewriting it differently, where we our intercept, our y naught is at the front by convention, and our two slopes with our departure hour and day of month are just these parameters, which would be the ax and the by. So this is nothing too unfamiliar for all of you mathematically through the Math 20 series, because z equals ax plus by plus c winds up giving us a plane. So, some like three-dimensional space with a plane. Which on this next slide is a nice pictorial representation of that plane in three-dimensional space that we had from last lecture. So the question is, what do we need to do in order to go to multiple features and get into higher dimensions? And more importantly, how do we generalize this problem so that instead of thinking about one or two or three features, like x1, x2, or not, we're going to think of it in terms of like d features, just like we have n number of rows. And really, in order to do that, we've got to kind of think about this new idea of something called a feature vector. And a feature vector is pretty interesting, because a feature vector allows us to encapsulate each observation of our data and all the features that are relevant to making that prediction for that observation. So for example, in this case, let's kind of section off minutes. Let's use yellow. So minutes are y. So these are the predictions. So the y's. And row, this is just the observations, just a count. But our feature vector is the group, the pairing of independent features that make up one observation. So in this case, we could say something like, well, real quick, I'll put these are our x's, but we have how many feature vectors here? Well, we've got 3 rows, so we're going to have 3 independent feature vectors, because remember, each feature vector encapsulates every single feature. So, and going forward, there's going to be some, I don't want to say complications, but there'll be some, in machine learning, nomenclature and how you kind of write out your notation definitely differs from textbook to textbook, but we'll try using a pretty standard approach. But some of the x's we'll have subscripts and superscripts. So for now, just kind of try and keep an open mind. But our first feature vector, and we have our second feature vector, and we have our third feature vector, and this is going to be 8.45 and 22 and 8.90 and 28 and who would have guessed it, 8.72 and 18. Again, this is represented here. So these are our 3 feature vectors, and it's important to think about feature vectors because they're a way to encapsulate all the information needed in order to make a prediction. So for example, our first observation, row 1, what we're saying is the feature vector represents the pieces of information that we would need to have in order to make a prediction for how many minutes it would take. So depending on what time in the day we left and what day of the month it was, with these 2 pieces of information, we can try and make a prediction on how long it will take us to get to school. So this is the reason why it's important to be able to encapsulate our x's in terms of feature vectors. And you'll see that it kind of makes a little bit of sense when we talk about utilizing the design matrix in subsequent slides. All right, so remember we have this idea of the hypothesis vector, and the hypothesis vector encapsulates everything actually needed to make this prediction. So that's also going to include some arbitrary bias or W naught or y-intercepts. But the hypothesis vector includes all of these things that we will need. And more importantly, it is a way for us to really think about how we go about making predictions. So what do I mean by that? Well, let's think about what's actually needed here. We have our, we have our hypothesis vector here, and this includes all of our predictions, right? Because we have n observations and we're going to make n predictions. So our feature or our hypothesis vector includes all those predictions. And in order to do that, we're going to need to take the idea of the design matrix, big X. and we're going to need to multiply it with the parameter vector. So that would be use purple for that, and this is our parameter vector. So every single one of these rows here in our hypothesis vector includes all this information needed to make a prediction. That includes our y-intercept, or what's commonly known as a bias. We'll see that term a lot more. And it also includes the individual weights needed to multiply the individual or independent features that we have. And we're going to have as many weights as we have features. So the hypothesis vector really encapsulates the design matrix multiplied by our parameter vector. And let me just put this down, our parameter vector, and then our design matrix, and then our all predictions. So that's pretty much what's happening. And for our design matrix, remember that this is going to be a n by, in this case, we have our W naught, W sub 1, and W sub 2. So this will be an n by 3, and this is going to be a 3 by 1, because you need to be able to do this multiplication, and the inners need to match. And what's also interesting to think about is we have in our design matrix, of course, we have our number 1 right here, which is our y-intercept. But we also have departure hour 1 and day 1, which correspond to the first observation. Then we have departure hour 2 and day 2, which correspond to our second observation. Oh, and we have, of course, departure hour n and day n, which corresponds to our nth observation. And what do we have here? We have our observations 1, 2, and 3, and we have our feature vectors, which are, in this case, 8.45 and 22, which is this feature vector right here. So really, in the design matrix, everything in the design matrix beside these ones is just a feature vector. So maybe let's say our first x1 is 8.45 and 22. So we have, not this in blue. Let's just call it departure R1 and day 1. So our feature vector, of x1 is equal to departure hour 1 and day 1. And you'll notice that that is just x1 transpose, which is this right here. And this blue is not the best to use. We'll just go ahead and make it red. So this is the connection between the feature vectors and our design matrix. Our design matrix is made up of a bunch of feature vectors that are transposed. And then, of course, we have that extra bias right here, but that's the connection. And that's important because these weights need to be multiplied into each row of our design matrix. And in order to do that, we need to have the feature vector constitute the entire row, because if we don't have that, then our predictions wouldn't mean anything. We would have, first of all, we wouldn't be able to do this anyways, because these dimensions wouldn't match. But it'd be like saying our first observation is departure hour being the bias times W1 times departure hour, and W1 again, or W2 times departure hour again. So that wouldn't make any sense. So the structure has to be like this, because we need to be able to take all of these and multiply them through with all this in order to get our prediction for that observation. And again, this is one observation multiplied by the weights for each observation, and then that's how we get this prediction. So that's where this kind of how we get to this type of structure, I suppose you could say. And in a more easy to view version of this, maybe this kind of helps a little bit. We have our design matrix, and then we have our commute times, which are this y our y vector or our prediction vector or observation vector. All those names are fine. And in order to determine what these w's are, because these w's are going to okay, the one is always going to be a one. The departure hour and the day are going to be the same because this is the data that we collected. So departure hour 1 and day 1 are set things. Departure hour 2 and day 2 are set things. The stuff that's changing that we're trying to find out are these weights, because then eventually when we get new data, we're going to take that new data, departure hour, Q and day Q, or something from like in the future, and then we're going to multiply those by our parameter vector, which are the weights that we learned, and that's how we'll get a new prediction for the future. And that's why we need to use the solution to the normal equations is how we get those W parameter vector, how we get the parameter vector. So that's important to keep in mind. And it's also good to know when we're trying to find what that W vector is that there's always guaranteed using the normal equations to be a unique solution, like a unique W vector, if and only if X transpose X is invertible. And what does that mean that's invertible? Well, if we take the determinant of X transpose X and it's non-zero, that means that it is invertible. And that what that tells us is that the columns of X are all linearly independent. And if all the columns are linearly independent, you think back to your, I guess it also means that it's what is it? I think positive definite. Thinking back to the linear algebra, I believe it also, positive definite. I believe that's true. But what that means is that this is especially useful for linear regression, because if we know that the columns are linearly independent, then we can have a unique solution for a W vector or a parameter vector. Now, if it's not invertible, then that means that there doesn't exist a unique solution. But it also doesn't mean that it's that this is useless and it breaks down. It just means that there are potentially, I suppose it means that there would be, I guess, infinite solutions that we could use, and any one of them would be guaranteed to get us the best fitting, in this case, a plane, because we have W naught, W sub 1, and W sub 2. But that's why if it's invertible, we know that there is one W star. If it's not invertible, there could be infinite W star vectors that we could learn. All right, so let's go ahead and talk a little about some of the new notation we'll need for multiple linear regression. We're gonna need to keep track of many features now, and we're going to need to have some way to generalize that. I know in practice we could have hundreds or thousands of features, and for many machine learning models, thousands of features is fine. Deep learning is a great example of that, possibly. However, in linear regression, having thousands of features would be absolutely terrible, and advised to have as little features as possible when it comes to linear regression. Is generally a good rule of thumb. Linear regression doesn't do very good when it gets too complex. As a bonus, though, learning linear regression in depth like this will give you a lot more to appreciate when you start learning how to parameterize or regularize your models, and that's when you begin to apply penalizations to them for complexity, and allows you to fine tune them. So this is all good stuff. But before we get to that, we have to be able to have a proper notation for dealing with multiple linear regression, because we want to be able to have many training examples. We're also going to start to begin to talk a little bit more in machine learning parlance for the most part, but instead of observations in our data set, right, the rows of our data set, which observations has much more of like a statistics, from a stats class kind of connotation. Training examples is the preferred term in machine learning, because we are using the rows in our data set as training examples from which to learn our parameter vector. So we will provide training examples because they're the pattern that we're going to learn from. And in order to do that, we're going to need to have a way of talking about a number of features and the feature's location within the training example. So note that if you have like x2, this is an exponent. And if you have x2, not an exponent. So make sure that you see that and realize it because you don't make a mistake on an exam or anything. So these are not exponents right here. These are talking about the number of features that we have. And now we're going to talk about features in terms of D features. So for example, we would have x1, x2, and x, you guessed it, D. So you can kind of think of them as placeholders for variable names or feature names. So x1 is departure hour, x2 is day of month. And we might say things like, well, let's put down maybe an example. X5, 4. So what is this? How do we say this? This represents the value in our data sets of the 5th feature and 4th training example. Oops. Okay. So how we would say this, it'd be, of course, 5th feature and the 4th training example. There's not like you wouldn't say like x sub 4, 5, or x 5th sub 4, anything like that. Anyways, these things, this kind of notation is also just, the way we're doing it here, but there are other ways that people use to talk about these things. Anyways, going forward, this is what we will use. So now that we have a way to describe any value in our training data, we want to be able to. We really like doing shorthand stuff. So before we talk about augmented feature vectors, let's think about this real quick. So this is our hypothesis function for our x feature vector. And this is saying that in order to make a prediction for our feature vector, we're going to take our y-intercept weight and, of course, multiply it by 1. So it's just whatever the weight winds up being, whatever the y-intercept we learn is. And we're going to add that to our next weight and our value for the first feature, so on and so forth, to where we have the D weight multiplied by the value of our D feature. So this is a lot to write. And as a shorthand, we want to be able to do something like this. The feature vector dot product with the augmented feature vector. So what is an augmented feature vector? Well, an augmented feature vector is our feature vector, except we add a 1 on top. And the reason why we want to add that 1 is because if we don't have that 1, then the dimensions don't match. We can't very easily do our parameter vector dot product with our feature vector. So we just add the 1 there because the 1 really the 1 from our design matrix isn't a feature per se. Like there is no feature in our training data set that we have, right? Like this is our training data set, departure hour, day of month, and then the Y's are minutes. There's no 1s here, right? Like 1s isn't data we've collected. We're using those 1s because we need it in our design matrix in order to satisfy the normal equations to give something to multiply our y-intercept for. So that's all we're saying. And if we look at our feature vector now, you'll see that this is the first feature, second feature, all the way to the D feature. So if we had an actual example of this, we could say that, x1 would be, I believe we use departure hour first and then day. So is equal to departure hour, x2 is equal to day of month. And we're going to have any number of other features in here for however many features that we have. So perhaps like x3 could be, you know, I don't know, whatever want to say, you know, average tire pressure. And because I already had a hard enough time picking what a third potential feature could be, our fourth one could be, you know, how many time spent, you know, eating breakfast or something. Presumably, these are good features and important features to use, but oh yes, I'm sure that was an easy setting I could have hit before, but whatever. So we have our feature vector, which is a d by 1 size, and when we have an augmented feature vector, it's just d plus 1. And the same thing goes for our parameter vector, which is just going to be, again, a size of d plus 1 by 1. This is why we add that, that 1 there. So how does this look? Well, we've already kind of talked about this, but just to make it explicitly clear, I'll use that one. Our 1 and w sub naught is right here, and then this guy is right there, and then so on and so forth, all the way down to RD, which is why now them having the same shape, we can write it like this. And also important to note, just in case this isn't obvious, all the values in your feature vector are just constants because they are values from our training data, like the raw value, these things. These things. Okay. So let's think about the general problem that we are trying to solve here. We have n data points and we have d features, and I'll just highlight that. We have n data points and d features. N data points is really just our, well, let's write like this. The size of our training data. And I just don't mean the size, maybe dimensions might be better. Because that encapsulates the number of observations that we have, or the number of training examples we have, and then the size, the number of features that we have. And so every x sub I is a feature vector of d features. So our feature vector, the amount of them that we're going to have is going to be equal to the number of training examples that we have. So in this case, this is one feature vector, and this encapsulates all of the x's for that training example, and an x for each of our features. And the question is how do we find our w stars, our parameter vector? So w naught star, w1 star, all the way up to w d star. So w naught star, w sub 1 star, all the way to w sub d star. So we want to find these. This is the most important thing, and in order to do that, we need to create a design matrix, and we need our observation vector. So the observation vector is given to us. This is our y's, or the things we're trying to predict. The design matrix is something that we create where we just add a column of ones, and then we insert into it all of our feature vectors. And then we create this augmented, we did it right here, this idea of an augmented feature vector. We do that for all of our features. And that allows us to solve our normal equations. So we package all of that into this now. And just so that we're on the same page, would be best to, well, let's talk about the dimensions of this real quick. This would be n, the number of training examples that we have, by d, the number of features we have, plus 1 from our column of 1s over here. And we'll use purple and green, yeah. We have here, so I'll do this one. So that's important. And then we can also just circle one of these. And that's important. Okay, so what do these two, what does each row in our design matrix and each column in our design matrix represent? Well, each column in our design matrix is a feature by itself. And you can tell that because 1, 1, 1, 2, 2, 2, all the way to D, 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 and we have D features. So this is just a single feature. So for example, pick any of these ones, departure hour. And our rows in our design matrix is equivalent to a training example. With the caveat, well, okay. It's incorporates a single training example insofar as this stuff, but it also includes the 1, so what we need for determining W naught. So it's a single training example plus a 1, which is equal to all the, essentially all the data we need. All the data might not be the most accurate word here because it involves that 1. So all the stuff we need to make a prediction. Okay. And so by designing the design matrix, as well as providing it in terms of an augmented feature vectors that are transposed, because again, remember, this is a vector of augmented feature vectors where each feature vector is transposed, because feature vectors by themselves look like this, and then so they're columns, and we need to have a list of them, or a vector of them. So now they've been transposed in like this to being like that. So we need these things, and design matrix with our augmented feature vectors, along with our observation vector, will allow us to solve the normal equations and find either a unique answer if it's invertible, and if it's not, we find many possible answers. So when we talk about parameters, and parameters are, so this is again some different terminology from the world of machine learning. When we talk about parameters, these are the W sub 1, W sub 2, all the way to however many features we have. No, it does not include the W sub 0, that's the intercept. But the W sub 1 and W sub 2, all those are called, well, we've been calling them slopes a lot, especially when we're dealing with just a single line with the simple linear regression. In machine learning, they're typically called weights of your feature weights, and that's especially true in like deep learning neural networks. However, in linear regression, it's pretty common to call them coefficients, and specifically like beta coefficients. That's the terminology used typically in most textbooks. But here, weight, coefficient, slope all mean the same thing, and I'll probably use all 3 terms. So this is the data that we're using, but these W's here are the coefficients or the weights. So weights, coefficients, or slope. And then in the W naught, we've been calling it an intercept, but it's typically known in machine learning terms as being the bias. And maybe I'll just add a little bit of this is the typical term used and the typical terms used in machine learning context. And why is this the bias? Well, it's because, well, one, if all of our weights were 0, and these all went to always for 0, then the bias would be our prediction, right? Because this can't go to 0. So the bias gives us a way of at least making a prediction. If the y-intercept was 0 for some reason, then we would just predict 0. But that typically is never really, or is often not the case. For example, like if you were trying to predict housing prices, it wouldn't make sense to have a y-intercept of 0 because is the cheapest house you can find 0? No. So y-intercept, or the bias tends to have, arguably, when you find a best fitting line based on data that you collected from the real world, the y-intercept of the bias tends to have some real world connotation, and it's literally just a constant value that we are applying to the entire model. So, for example, if you had a line, this was 0, and this was like, say, 10,000, we're doing the housing prices. 10,000 is just the bias that we would apply to every prediction that we made, because this line, instead of being like this, has been moved up by 10,000. So every single thing that we could predict, any of these predictions have now shifted up by 10,000, which is why it's called the bias, because we're biasing the model by 10,000 units, or whatever that value would be. And that's how we call that the bias. Okay, so let's talk a little bit about interpreting parameters. Okay, so let's say that let's have a short departure from the average commute time problem. Let's talk about predicting sales. So in our data set, we have our imaginary data set. We have 26 stores, and in those 26 stores, we have a data set of these features: net sales, square feet inventory, advertising expenditure, district size, and number of competing stores. So the first question that we want to ask is, what is the total number of observations, or the size of our training set? So in this case, we have 26 stores. Let's just assume that we have, like not each store has its own data set, but this is just one comprehensive data set. So our N would be 26, because we've got 26 stores that we've pulled data from. Now, our D, the number of features, is either one or two things. It can either be 6 or it could be 5. Why? Because we have 1, 2, 3, 4, 5, 6 things here. And why is it could be 5? Because we have to decide, is net sales, which is what we're predicting, a feature? And the answer to that is no, it is not. So D in this case is 5, because sales is what we were predicting, not a feature. So we want to predict what the sales would be given these 5 features. So these are our X's, and this is our Y. And a good way to start with this type of a problem, and a great way to start with linear regression modeling, is something called, one in at a time. Because when you're doing linear regression, you can run the model, add a feature, run the model, add another feature, because it tends not to be a very computationally expensive model to run. And so you can add features and see how that changes the feature importance and how your parameters change. You can also start with all your features and just take one out at a time and see what happens. These are called ablation regression studies. But here we're going to start with 2. We're going to start with square feet. So square feet and competitors, number of competing stores. So in this case, our first model is 2. So we might actually use this example for an in-class demo. I haven't decided yet, since I'm still working on the demos. But one thing that we want to think about is, how do we actually deal with this data before we start doing a regression model? So net sales, right, is its own thing. Square feet, inventory, advertising expenditure, district size, and number of competing stores. Let's assume that we've trained our model and we found our W vector, or our parameter vector. And let's assume that our parameter vector gives us something. We will start with D equals 2 for this example. So we have our parameter vector, which is going to be W naught, and then W sub 1 and W sub 2. And let's just say that this is equal to go 10, and then maybe square feet could be something like 45, and competitors could be something like 0.012. Now, this is what, by solving the normal equations, we found our W vector to be. So in the previous lecture, I had kind of offhandedly said, when you have something like this, it's often very possible that this as a feature is not really doing very much and we can either replace it or remove it. Now, that is true. However, that is true if the data that you have has been standardized or has had some sort of transformation done to it to make it so that all the features are expressed in terms of the same kind of magnitude of effect. The reason why is that, let's look at number of competitors. How many possible competitors could our 26 stores each individually have? 1, 3, 4. Maybe these are rug stores. How many rug stores are there on the corner? There ain't more than the number than there are Starbucks. So it makes sense that this number could be very low. And what about square feet? Square feet tends to be quite large. Instead of being in the number of like 1, 2, 5, 6 competitors, square feet tends to be in the thousands, or for commercial or even industrial real estate, it could be in the tens or hundreds of thousands even. So what we're doing is we're trying to predict a model or learn a model, and the solution to the normal equations is giving it to us in terms of the magnitude of square feet and competitors being completely different. So how do we deal with this? Because this might not be the correct answer if we were to have, let's say for some reason, square feet was in terms of like tens of square feet for just some weird reason. Then competitors and square feet want to be much closer together. And so maybe we'd have something like 10 and 2.5 and 0.21. And these numbers are a lot closer together. So what's happening is that we want to be able to change our data a little bit so that the numbers want it being closer somehow. Whatever closer means, we'll find out, because we want to know which features are important and which are not important. Consider, for example, I know we just talked about it, but an example where you have sales and we're talking about the Japanese yen versus the US dollar. The Japanese yen is orders of magnitude different than the US dollar. So that would change our hypothesis function quite a bit, because there will be a much larger weight applied to the yen because it turns out that the yen is a much larger number. So one way to solve this, there are at least a couple ways to do it, but the most, probably the safest and the best option to typically do is standardize your features. And by standardizing, we mean standardizing each column of data. So not feature vectors, right? I don't want to standardize, in this case, square feet. I don't want to standardize square feet and competitors together. I want to standardize all the square feet for all our training examples together independently, and competitors together independently. That will allow us to have our feature in terms of having a mean of 0 and a standard deviation of 1. And this is a crucial process because it ensures that our features contribute equally in our modeling, and it improves the stability of our models. These are optimization algorithms, and standardized data can lead to faster convergence. There's some improved stability in terms of predictions. So they're pretty important. And this is something that you do in, it's not just for linear regression, but across all machine learning models. Standardization can be a very important step. Obviously, for different types of data, there's different things you can do, different types of standardizations or normalizations that you could take. But standardization, and this is something that you've probably heard in DSC10, is just taking the feature and turning it to a mean of 0 and a standard deviation of 1. So that's what we'll do. Okay, so let's go ahead and talk about feature engineering and data transformations. Okay, so let's finish off by talking a little bit about feature engineering and transformations of our data. So in this example, we have miles per gallon in horsepower, and there's of course nothing that's saying we can't create a line to fit this data. should look maybe something like this. But there's also no doubt too that there seems to be maybe perhaps some other type of pattern here, and perhaps it would be better to fit this data with some sort of like quadratic hypothesis function. And maybe that's not the best either, but it's good to know that we have options, especially when we're presented with interesting patterns in the data that suggest nonlinearity. So how would that work? Could we, doing the same thing that we've been doing, design a hypothesis function, which has nonlinear components to it? What would that even look like? Well, just to be clear, this would be oh, that's fine. So really, with our hypothesis function, we're really following some sort of pattern that you probably can see by now, and that's the case where we have some W naught, and we don't need to have the W naught, but it's often very useful to have it, a y-intercept or a bias. But the important thing is we have some W naught times something. In this case, it's typically a 1, so it's just W naught, plus W sub 1 times something, plus W sub 2 times something, so on and so forth. So this has been kind of the pattern, and a particular importance in the pattern is that there's no W's in these locations. These are just constants that we multiply from our data set. Think about the feature vectors. And it's, so as long as we fit that pattern, there's nothing stopping us from doing something like this, where we have, like an exponent. Now remember, this is, maybe put this up here, I'll do a different color. This W2x squared is not equal to W2x2, right? This is this was talking about which feature. This is actually exponentiation. So I want to make that clear. Remember that. So in the case where we're trying to think about horsepower, it might make sense to have a feature in our data sets, which of course is horsepower. So this could be, we could say that xi of 1, which is equal to x sub I, is equal to horsepower, or it is horsepower. And we could also say that xi2, so a new feature that we're creating, which is equal to x sub I. I suppose I'm just rewriting the same thing. But this would be equal to the feature of, it's fine, x sub I squared, which is equal to horsepower squared. And that's perfectly fine to do. The main thing is by following this pattern here, we're creating linear combinations of our features. That's the key. And by doing that, by creating these new features, this is feature engineering. This is sort of the, creating crafting, creating handcrafted features has always been a staple in machine learning, and it was an extremely important and big part of machine learning until deep learning came around, and or came back to the degree in which it has come back. So, for example, like in the old computer vision research time, people would create these like features, handcrafted, very elegant, like face detection features, features to detect the edges or boundaries, and those are much more complex than just perhaps squaring something. But deep learning, that there was not that need to craft those features anymore. Not to say that this is true in all cases, but that's kind of a new thing with deep learning, is that there's a lot less feature engineering in the traditional sense. But anyways, not going on to a tangent. So this is going to give us a quadratic hypothesis function when we do this squared here. And what's happening is, we're creating a design matrix now, which is still pretty familiar to what we have. So we're going to have this big thing here. It's still going to be, in this case, an n by 3, because we have 1, 2, 3 features. And so the first one will just be a series of 1s, and the second one, and the third one. The second will just be basically horsepower 1, horsepower 2, and then horsepower n, and this will be horsepower 1, horsepower 2, horsepower n. Of course, these are now our squared features, and notice they really are squared, not an exponent. So 2, not 2. So it really is an exponent. And as long as we have that design matrix, and we also have our W vector, which in this case are going to be 3 things. So W0, W1, and W2, which corresponds to that, and to that. So that for each row in our observation matrix, we're going to multiply it by the entire W vector. So as long as we can construct such a design matrix, it doesn't really matter if our feature has an exponent in it, let's say, as long as it follows, again, the pattern of linear combinations that are being added in our hypothesis function, then we can use the normal equations to solve this, That's the key thing here. And it really doesn't matter. We can have to the third power here. This is this is fine, as long as it's if we can put it into the form of our design matrix times our W vector, and we will get our predictions or our y hats. So that's perfectly fine. In this case, our design matrix would be we have 1, 2, 3, 4, so this would be an n by 4, and then our W vector would be a 4 by 1, and that's fine. Same thing would work for this as well. Down here, it looks odd, but we still have 1, 2, 3. Note there is no W0 here, so in this case we would have something that would look like our design matrix would be, let me draw a little bigger, 1, 2, 3, so this would be a n by 3, and then our W vector would be W1, W2, W3, and this would be, let's see, 1 over x squared, that'd be x1, and then 1 over x2 squared, 1 over x3 squared, and then this would be sine x1, sine x2, sine x, whoops. In this case, this would be n. I can write this a little bit nicer. So 1 over x2 squared, 1 over x n squared, sine x of n, and this would be e to the x of 1, e x of 2, and e to the x of n. So again, as long as we are following the pattern, this is fine. We can design, we can craft a design matrix and a weight vector, and off to the races with our hypothesis function. Because remember, these two things in concert gives us our hypothesis function. So that is the process of feature engineering. It can be quite interesting, but is an important part of machine learning, and it allows us to do a lot of interesting stuff. You'll see eventually, especially things like encoding categorical information is key, like one-hot encoding. Things like that, where you're trying to take like the day of the week maybe, and then encode it as an actual number that computers can understand. So 7 days might give you 6 columns, or just as an example, we might have a feature I have a feature which is Monday, Tuesday, Monday, Wednesday. And let's say this is all that it could be. Monday, Tuesday is just 3 days of the week. This, could be transformed into, is Monday, is Tuesday. And so now this would be, is Monday, 1, 0. That's a Tuesday, 0, 1. We have a Tuesday, 0, 1. We have another Monday, 1, 0. And what do we do for Wednesday? Well, a lot of people might tell you that you need to have another column here for Wednesday, but we can encode Wednesday as just 2 zeros. It's neither Monday nor Tuesday. So this is how you can feature engineer this. So maybe this one's Monday, and then that's this. And then just to make it clear, Wednesday, that's this one. So there's lots of different things you can do with feature engineering. It is extremely useful, especially in linear regression. And we can use feature engineering to bring out some nonlinear properties within our data set if we see those, like in the example of horsepower, miles per gallon. I don't want to go in depth in this one, but there's just an example of taking our sales data set from a few slides ago, and we have here this kind of scary looking hypothesis function, but it's okay. We can still create a design matrix for it, and we can still create our W vector, and we're good. So that's fine. And yeah, I think this is just a, it's probably a good place to, I think we talk about this. The whole point that we're trying to bring back to is we see this sort of pattern that I talk about. Might be a good thing to write down, where it's some W plus W2. And these things wind up being, a linear combination. So linear combination. And if we have this pattern, we can design we can create a design matrix. And we can design a W vector, parameter vector. And if we can do those things, then we can get our hypothesis function. And if we can do that, then we can define mean squared error. And if we can define mean squared error like that, then we can use the normal equations to minimize mean squared error. And if we can do that, then we're good. Again, as long as, if this is invertible. Or I should say if x transpose x, if x transpose x is invertible, then we have a solution. For W star. If not, we get infinite many solutions. But that's the important thing to take away from this. We have this new idea of mean squared error. We're able to do this if we can define a hypothesis vector, which is a design matrix and a parameter vector. If we can do that, then we can solve for the normal equations. And if we can do those things, then it really doesn't matter what goes in here. This is just a linear combinations. And that's good to go, if we have that. What we can't do, though, is something like, I suppose I should use a different color, but this is not good. This is not good. Why? Because this is, the W is an exponent. And in this case, the W's are in this sine function. And these are not linear combinations anymore. These are, weird operations being done to our w's, which is no bueno, not good. So what we really need are these linear combinations. And if we have that, then any arbitrary polynomial stuff can happen in here as long as the w's are clean. It's something, So yeah, we need clean w's. In this case, these w's are dirty. So that's a really key thing to think about. And we'll go ahead and end it here, and we will pick up this next time with a little bit more on transformations, and then we'll start getting into gradient descent and why gradient descent is such a useful thing for minimizing stuff that's not just linear and stuff that we just can't use through these methods that we've been learning. And gradient descent really becomes a hallmark for minimizing many more advanced machine learning models. So it was a great thing to learn.